Welcome to the Bytecode, where we look at smart contracts with the people who wrote them. I'm your host Shafu, and today's episode is with Vectorized, who's gonna walk us through some of the Solady contracts. Vectorized, thanks for taking the time, man.
Hi, thanks, Shafu. Nice to be here. Okay, so today I'm going to go through some of the contracts in Solady in no particular order. Okay, so some of the contracts that I think are more interesting are okay. Let me see. I don't want to pick something that's too hard to present. So I will pick ERC20. Okay. ERC20, maybe lib clone, and I think ECDSA. And maybe one more that is not here, which is libzip. Libzip. Yeah. So hopefully I can present all four contracts. So right now, Solady is going through a Cantina audit. So Cantina is a security marketplace set up by Spearbit DAO. And now Spearbit is auditing Solady. And their findings are quite good, but luckily we don't have anything too serious. Mostly or many tiny nitpicks and compiler, like some compiler edge cases that we have to be careful. Okay, so for ERC1967 factory, I think there's an article somewhere out there that describes it in much better detail than I can describe in this video. So I go through the stuff that are like gone through for the first time, like ERC20, libclone, ECDSA, and maybe one more called libzip. Okay, so let me visit the ERC20. So under Solady, you go to source, you go to tokens, you click here, there's an ERC20. So the thing about Solady is that the entire contract is mostly implemented in inline assembly. Okay, you can see that everything is assembly something something, assembly something something. Okay, because we are using inline assembly, we can use a custom storage layout. So instead of using a mapping, like in normal Solidity, we define our custom storage scheme, which allows us to create a more efficient way to map keys to values. More efficient as in down here, some of the keys are like addresses, and in assembly, addresses might have dirty upper 96 bits. Okay, so the Solidity compiler doesn't guarantee that the top 96 bits will be clean for any bytes that are smaller than 256 bits. So we have, because we are using assembly and we can do all these like crazy tricks, we can somehow define a mapping scheme that can automatically ignore the upper 96 bits. So we don't need to clean them. Okay, in Solady, we don't really like to use constructors because one thing is we want our contracts to be compatible with normal contracts and also compatible with proxies. Like you want to make a minimal clone or you want to make a upgradable contract, you can use the same code. There's no need to have one code base for normal contracts and one code base for upgradable contracts like OpenZeppelin. So everything just in one repo. And to do that, we have to make the decision to do away with the constructor. So everything is by initializers. So in order to use ERC20, you have to overwrite the name and you have to overwrite the symbol to return something. You can't just constructor name and symbol decimal. You can't do that. You have to overwrite this. So there's no constructor. And this design choice also makes the code more efficient because instead of storing the name and symbol in the storage, if you just override it to return a constant, the compiler can do some tricks such that you save some S stores and some S loads, and your code will be smaller, more efficient, so on and so on. So it's like you have the benefits, multiple benefits. Your code is compatible for normal and upgradable contracts, and also your code is more efficient. Okay, so all these are just like the assembly stuff to load from the storage.
I have a question, Vectorized.
Yes.
Why in the decimals does it return 18? Why return something there?
Why do we set it to 18?
Yeah.
By default, it returns 18. There are some naughty tokens like USDC that return 6.
Yeah.
Which I don't know why they choose that, but anyway, if your token returns 6, then you should override it because there's a virtual down here. There's a virtual keyword. You can override it and return 6. It's okay. But by default, we return 18.
Okay, because so you just assume most will use 18.
Yes, most.
Okay.
Most. Okay, so I just let me see what findings did Cantina or Spearbit find. Issues. We are C20. This is bit true. That's good. Okay. Memory unsafe assembly is not future proof. Okay, let's go through the easy one first. Underflow check can prevent allowance decrease. Okay. This is an interesting finding because it affects Solady and also affects OpenZeppelin's contract because we are using a design based on OpenZeppelin. We have a function called decrease allowance, which is inspired by OpenZeppelin, and this function will revert if the number you want to decrease is more than the current allowance. So Philology, who is one of the auditors, he's suggesting that this decrease allowance function is not very safe because it can be front run. Like if you want to put a decrease allowance, some guy can see your transaction in the mempool and do some stuff to make your transaction revert. Okay, I think there's too much to go through here. All the tiny specifics. Okay, so what Philology suggests that instead of reverting, why not just try to reduce, and if it's going to be negative, you just round it to 0. You just cap it off at 0. So it's like instead of like reverting, if it is going to be negative, you just cap it at 0. So okay, I think he doesn't recommend something. But anyway, the fix is in one of the PRs. So how are we going to fix it is we are going to add a new function called decrease allowance until 0. So what this function does is that it's like decrease allowance, but instead of reverting, if difference is more than what the current allowance is, it will just round it to 0, cap it off at 0. Okay. Never mind. Let me just show you the code. Control F, decrease allowance. Yes. So it's down here. Instead of reverting, we just set it to. Okay, this is just some assembly trick, which means that if allowance before is less than difference, then multiply the. Oh, wait. Yeah, the code is correct. Yeah, correct. Okay. Yeah, so this is the fix. The other finding on ERC20 is, yeah, this is something you have to deal with when you doing assembly, like memory safety. So before the current code, there is a thing called the domain separator, and we use some tricks like not allocating memory and somehow abusing the free memory pointers. Okay, this proof of concept is like it's so complicated. But never mind. Okay, so the way to put it is that right now with the current compilers, like Solidity 0.84 all the way until Solidity 0.8.21 is safe, even if you use VRIR. Okay, but in the future it might not be safe. So that's what he's saying. So the fix. Okay, so what's the fix? The fix is that we make the function even more efficient by just somehow inlining the entire domain separator calculation. So we don't need to like do some free memory pointer tricks to avoid this this possible edge case in the future. Yeah. So we just like manually copy and paste the code in. Yeah, I think that's pretty much it for ERC20. There's a lot of like random tiny stuff. Oh, these are the tests. Okay. Are there any questions you have?
Not so far. I would need to
Okay.
look into a bit more detail into this. But
I think the report from Spearbeat will come out next week. But now I don't want to go too much into ERC20 because it's like you just copy and paste it. You just import and overwrite the stuff and then you just deploy. It's not a very it's not something you appear into like too much. Okay, so other than ERC20, let me go through okay, lib clone. Lib clone is another interesting contract. Okay, source, utils, what's it? Lib clone. Okay, so lib clone is Solady's minimal proxy library. There are three kinds of minimal proxies we have. One is the 0h minimal proxy. One is the push zero variant minimal proxy. And the last one is the clone with immutable arcs, which is kind of like a minimal proxy. But we have something different here. We have a slightly different implementation from the original. So we have a method in the bytecode that emits an event if you sense if without having any core data. Okay, so this in this contract, no, in this library, everything is like written in bytecode directly. Yeah, written in bytecode. So all these funny mumble jumbles are just carefully written bytecode. And here is all this gigantic comment table is just explaining what this bytecode is doing. So there is a 0h version. There is also the push 0 version, which is the most efficient, but only supported on mainnet Ethereum right now. And after a lot of convincing, I managed to get Etherscan to automatically verify any push 0 proxies. So now it's actually very useful because Etherscan supports it. Yeah.
Nice.
Yes. Then there's also the push with clone with immutable arcs. Okay, so one of the findings they have is that let me see what are the findings. I think it's a high, but I won't consider it high personally because okay, I will explain why. So in the clone with immutable arcs, there's a data. Okay, you can somehow encode the data into the proxy. And the thing is that if the data is too big, you can somehow corrupt the proxy bytecode. Yeah. Yes. Okay. Yeah, so there's no check on how big is this thing called the extra length. Yeah, so if this extra length is more than 2 bytes, the proxy bytecode can be corrupted. And if it's corrupted, then if you accidentally send funds to it, the proxy will just lock up the funds because it can't do anything. The proxy bytecode is bad. If the data length is too big, why is it not likely to happen is that in most use cases, this data will be created by ABI encode. Like you will manually construct the data in the Solidity code by ABI encode something. So you won't expect this data to be like super big most of the time. So, but anyway, we have a PR that fixes it. Lead clone fixes and optimizations. So the fix is we're going to add a check. Add a check that reverts if the data length is too big. Yes. Okay, so we add this thing down here to revert if the data length is too big. So what this line is, we are abusing the return data copy instruction in the EVM to do an out of guess revert. And why we do an out of guess revert is because in this case, it's actually cheaper to because the way these instructions are laid out, it somehow shaves off like a few guess compared to if something revert. And normally we only do this if we are quite certain that the revert case is super unlikely. Then we will do this. If not, we'll just do a regular if something revert. Yeah. So this is the line that fixes the finding. Okay. I think 721 and 1155, the code is a bit too complex to explain with words. So I skip it. Okay. Then maybe I go through the ECBSA. Okay. So right now, okay, so ECBSA is a very simple library. It's like EC Recover, but slightly more efficient. So down here, we add a warning that you must never use signatures as unique identifiers. And this implementation does not check if a signature is non-malleable. That means what does non-malleable means is that we do some check on the S value that is less than some magic constant, which is quite some big number. Yeah, but we don't have to check here because we expect that people who use Solady are not like beginners who will shoot themselves in the foot. And also, the constant is quite big, so it adds a lot of bytecode. If you do the ECDSA properly, like you use a nonce in your signature and so on, the amount of bytecode you need to call to verify the signature is like super tiny. So basically, we just like copy the signature into the scratch space. We do some abusing of the free memory pointer and the 0 pointer, and then we restore it. According to one of the reviewers who also work at the Solidity compiler, he says that although this is not officially supported, but in practice is quite safe. It's safe, like currently for all the compilers that are released, it's safe. But in future, it should also be safe because it's like super unlikely that they will do some compiler that will understand what is happening to these two slots and like make the code unsafe. It's like very, very unlikely in the future. But right now, for all the compilers, it's safe. Yes. Oh man, I think I have gone through the contracts I want to go through. Okay, and one more contract I want to go through is this thing called the libzip. Okay, so let me go through. Under source utils, we have this thing called the libzip. And this contract is quite interesting because it serves like multiple purposes. You need to be an expert to know like what it actually does. But once you know what it does, then it's like super useful. So there are libzip has two class of compression and decompression. The first class is the LZ77 compression and decompression. That means it's like so LZ77 is like the algorithm used in zip files, and this is a variant that is more optimized for processing speed rather than the compression ratio. And we choose this version called the fast LZ because it is more compatible with like how the EVM works. It's more easy to code in EVM. So there are two functions. You can use it to compress like giant chunks of text to store in store2. So like if let's say you can maximum only store like 24 kilobytes of text in store2. If you do this, maybe you can store like 50 kilobytes of text. Yeah, you can store like twice the amount if you use the fast LZ compress function.
Yeah,
And this
Vectorized, I have a question.
Yes.
So what's the use case? Why don't you compress something off chain and then post it on chain? Why do the compression on chain?
Okay, this function is provided for completeness. For all purposes, I don't recommend using this on chain. Okay.
Okay.
But this one you can use it in your contracts. Like say you already compress it off chain, you upload the compressed data, and you have some token URI function that renders on-chain SVG or on-chain something. You can use this function to read the chunk of bytes and then call this decompress, and you have your on-chain SVG.
I see.
Okay. Yes. So we also provide an accompanying JS library that has the JS version of decompress and the JS version of compress. So you can do
Oh,
it on the JS side. You don't need to do it on
nice.
chain. Yes. The other useful thing we have is the core data compression. So in L2, the bottleneck is not so much of the storage cost. It's more of how much core data you're sending in the first contract. So if a contract calls another contract and the core data is very big, in the internal cost, it doesn't matter. What matters most is how much core data, how many bytes you are putting in the core data to the first contract in the transaction. So what Solady has this deep zip. There is a core data compress function. We also don't recommend using this on chain. We have a JS library for that. But we have also a core data decompress function. So this you can use on chain. Yes, so it decompresses the core data and then like you can do normal things with it. Okay, so the idea is that we want this core data compression and decompression to be a drop-in, but it's a no-fuss general approach. So you don't need to like have your custom functions to. Okay, basically, if you want to include core data decompression in your contract, you just have to include a receive function and a fallback function that calls this CD fallback function, and that's all you need. So if you send a core data to your contract and it's in the compressed form, then the contract will immediately know what to do with it. Yeah. Let me see whether I have an example on chain. Compress. One moment. Okay, so far, any questions? Yeah, okay. I go through it. I just show you how the JavaScript looks like. It's just a single file you import. Then it has all these like what we call the legacy stuff. Okay, this so it has the CD compress and the CD decompress. So how you use it is you simply CD compress the data. So the data is a hex encoded string of stuff. So if this is the like raw core data, it's like super long. And you can see there are like mostly zeros. So CD compress will somehow squeeze out all the zeros into a more compact form. We call it run length encoding. Yeah, so this is a compressed version. I think it's like many times smaller, maybe 3 times smaller. Yes, you just have to call CD compress and then you do a regular call to your smart contract. Yep. Okay. So let me see. Yeah, I think so are there still any other contracts? I think that's okay. 721 is under tokens. Okay, this contract is I would say is quite a headache to go through because the custom storage scheme is like is borderline insane. I would say it's insanity. Okay. So let me see what I comment to the reviewers. Hold on. Under pull requests, ERC721. Okay, so Sobon and Neteddy, they ask, why is the storage layout designed like this? Okay, so the reason why we do use this crazy layout is because we want to have several goals. One is to reduce mstore for transfer operations. So in the ERC721, before you make a transfer, you will check whether the caller is an operator, if not, whether the caller is an approved address, or whether the caller is an owner. So you have to do like multiple checks. And all these checks, you have to compute the storage slots and then load the value from the storage. So because you have to compute the slot again and again, like different slots again and again, we choose a very special custom storage scheme that somehow recycles the memory values from previous computations to reduce the mstore for like the total amount of mstores for transfer operations. So instead of like recalculating, like you can somehow recycle the previous values that you calculated. So another way we make it more efficient is that this custom storage scheme somehow cleans out the dirty upper bits with minimal operations, minimal upper bits of addresses. And the third craziest thing is that because in the future, Vitalik might push for EIP that will reduce the amount of how do I say? Like if you read consecutive storage slot, like let's say you read storage slot 0 and you read storage slot 1, right now the cost of reading is 21,000 gas. No, 2.1k gas, okay, 2100, 2100 gas. But in the future, with this Verker EIP, what Vitalik suggests is that if you are reading consecutive storage slot, it's actually quite efficient on the client. So why not reduce the read cost from 2100 to 100? So the idea is that instead of like using a keycard 256 directly for the storage slot, we somehow rearrange stuff such that the storage slot of token ID 0 and the storage slot of token ID 1 are somehow next to each other, such that we can abuse this future EIP to reduce our cost in the future. Yeah, so we are optimizing for the future. It's quite a weird concept. Yes. Whether it goes through or not, I don't have any expectation, but I feel that Vitalik has a very strong persuasive power on the Ethereum community. So whatever comes out of his mouth, it somehow like what he says become gospel. So I will expect that this EIP has a high chance of passing. Whatever Vitalik suggests might pass. Yeah. And something about Vitalik suggestion is that one day he also wrote a blog post on removing the quadratic memory expansion cost. And I was like, oh, this might have some effects on how we write a contracts. Because let's say some guest optimizer abuse this quadratic memory expansion cost to do an out of gas revert. Maybe it works now, but one day Vitalik say, let's remove it. Then the contract doesn't have the gut anymore and you can get wrecked. So throughout Solady, we don't abuse memory expansion cost to revert. We if you want to do a branchless revert, we will use the return data copy trick. Yeah, if you want to use 721 in your project, Solady 721, okay, let me see why would someone want to use this 721. Okay, so there is one feature called storage hitchhiking, which means that like the ownership slot, so the owner is an address, it only contains like 160 bits. So there's still like 96 bits left for other use case. So we allow you to somehow, okay, let's scroll down. Internal functions. Very simple. Storage is actually. Yes, okay. So extra data. Oh yeah, correct. Okay, so the ownership slot has like 96 vacant bits. You can somehow store extra data inside the 96 vacant bits if you want. And the balance slot, there are like, we somehow restrict the amount of tokens a user can own to 4 billion, which is 2 to the 2 to the power of 32 minus 1. And because of that, we have 224 vacant bits, which you can use to store whatever you want. Yeah, like how many tokens an owner has claimed in a whitelist. You can store it inside these 2 to 4 bits. Yeah, and also like the ERC20, the name and symbol, you have to override it. You have to override and return a constant. Yeah. So this is how 721 is. 1155 is quite a okay. 1155 we don't make the storage scheme that complicated. But the complicated part of 1155 is all these callbacks. Okay. If you see the regular soulmate 1155, you'll feel like, oh, so simple. It's just a do external call. But under the hood, Solidity does a lot of crazy stuff when you do a very simple external call. Yes. So all this external calling logic, this is the external calling logic for ERC155 batch receive. You see the amount of logic is like, you want to vomit. So 1155 is a standard that looks very simple on a high level. But if you go into the low level, it's very dirty. It's a very complicated standard on the low level. But from a high level, it's very simple. It looks simple. And that is the motivation wise behind one of the upcoming contract standards, which is ERC 6909. Because they realized that all these callbacks, like check on 1155 batch receive, check on 1155 receive, all this shit is like, it takes up a lot of extra bytecode and a lot of extra logic underneath the hood. So this standard, what essentially it says is that we just throw away all these callbacks, and if the user want to implement it, implement it. If they don't want, then don't want. So this is a standard I think should replace 1155. It's a much better standard. And it's by J. Raleigh. Yes. So Solady might, I think I will merge this once I review the code. But I need energy to review it, which currently I don't really have much. Yeah. Another upcoming thing in Solady is this Json Password. So I realized that currently there is no very efficient and elegant API for passing JSON on chain. So essentially, this library enables that. So Solady has a lot of libraries that somehow make it feel like writing a high-level language. Like some of the libraries that you think, like if you use JavaScript, there's a sort, there is a JSON pass, there is like all these string slicing, regex, and so on. All these are like we take for granted in other programming language, but in Solidity you have to implement all these from scratch. So we have a regretry, which is like out of the box. In like Rust or C++, you will have a standard map or standard set which has the regretry implemented for you. But in Solidity we don't have, so we have one down here. We also have deep sort. So sort is like insertion sort or quick sort. So a lot of functions we take for granted in other programming languages, somehow we have to implement from scratch in Solidity. And Solidity has like the aim for Solidity is to make Solidity feel like a high-level programming language without performance compromises. Yeah, there's also a min him dip. Okay, yeah, one of the things I think is very useful is a deep map. So in Solidity, if you want to like somehow pack numbers, like normally we'll have a mapping uint256 to uint32, and that wastes a lot of extra like storage space. So we have all these pack mappings for you to pack the values tightly together in storage. I think this is very good for storing timestamps and other small values. Okay, I think okay for safe transfer lib, if you want to transfer ETH or ERC20 tokens, I think you should consider safe transfer lib. It like does if it how to say it deals with a lot of the edge cases like gas griefing and so on and so forth. So if you are afraid of gas griefing, like you have a contract that you need to you have let's say you have an auction, you have an auction contract that when a new bid comes in, you have to refund the old bidder. But what if the old bidder is like some nasty contract that grieves all the gas? Then if you use a regular core transfer ETH, your contract is going to get wrecked. So we have a function called force safe transfer ETH. So it transfer the ETH with a gas stipend. But if somehow the target contract takes up too much gas, we will use a self-destruct to send the ETH. And this is preferred across if you want your contract to be, say, deployed across multiple chains, then this is a good function. Because if you have the wrap ETH contract, you know wrap ETH is like different chains have different wrap contract. Which is a super pain to test and code. And also if you hard code the wrap ETH address inside your contract, then you have to redeploy your auction contract at a different address across all the chains. So there's a lot of shit if you use the wrap ETH approach but instead if you use the force safe transfer ETH, then it's just like copy and paste out of the box. You don't need to care with all those intricacies. Everything is settled for you. Yep. I think that's pretty much about Solady. Thanks so much. Okay, so right now I think the audit is almost done. They are summarizing the findings. Okay, most of it is nitpicks, but very good nitpicks. Because some of them is like, oh, why didn't I think of this gas optimization trick? They point out a lot of useful gas optimization stuff. And so far the higher risk ones are like dealing with memory and yeah. I think the higher risk ones are dealing with memory and this okay, this is actually okay if you don't allow like users to arbitrarily set the length of the data, which is like most of the case. But if you allow, then yeah, it can be an issue. So I would say I'm pretty happy with the findings. It's like I don't need to really go out there and tell people to you know when you have a security finding, if it's a critical, then you have to contact all the users of the libraries, and it's a headache. So luckily we don't have anything down here that requires me to contact the users. Okay. Okay, thanks so much. See you. Bye bye.